Imagine the last human being who will ever live. Not a metaphor, not a thought experiment for a philosophy seminar. The actual final person. The one who draws the last breath our species will ever draw on any world, in any corner of whatever remains of a universe so old by then that the stars themselves will have mostly gone dark. Picture them wherever they are, and here is the thing that should stop you cold. Picture them looking up. Because they will look up. Humans always look up. It is perhaps the most consistent thing about us, across every civilization, every era, every language and landscape and belief system we have ever produced. We look up. We always have. And whatever that last person sees when they do, it will be nothing. Not darkness in the way you experience darkness when the power goes out or when you close your eyes in a familiar room. Not the comfortable darkness of a night sky salted with stars. Nothing. A void so complete and so permanent that the word emptiness doesn't begin to reach it. And here is what makes that image genuinely unbearable if you sit with it long enough. That last human will be alone in a way that no human before them has ever been alone. Not lonely in the way you have been lonely, after a relationship ends, or in a hospital waiting room, or on a Sunday afternoon in a city where you don't know anyone. Alone in a way that is structural, cosmological, baked into the geometry of the universe itself. Because by the time the last human draws that last breath, the observable universe will have expanded so far and so fast that every other galaxy, every single one of the hundreds of billions of galaxies we can currently see, will have crossed a horizon beyond which nothing, not light, not signal, not any conceivable message or probe or cry into the dark can ever reach them. The last humans will not merely be the only intelligent life they know of. They will be the only intelligent life the universe, from their perspective, physically contains. The rest will have vanished. Not died. Vanished. Receded beyond a boundary that the laws of physics have made permanent. Take a moment with that. We are used to cosmic loneliness as a romantic abstraction, the pale blue dot, the silence of deep space, the Fermi paradox sitting unanswered in the back of our collective consciousness. But those are the existential anxieties of a civilization that can still, theoretically, reach out. We have radio telescopes, we have the Voyager probes drifting outward, we have the James Webb Space Telescope staring 14 billion years into the past with something approaching hunger. We are alone, perhaps, but we are alone in a universe that is still, just barely, reachable. Full of light, full of signal, full of the photons of 100 billion galaxies still arriving at our instruments after journeys longer than imagination can hold. The last humans will have none of that. The sky above them will be dark, not because of clouds or atmosphere or the limitation of their instruments, but because the universe will have physically moved the light sources beyond recovery. The expansion of space, that quiet, relentless stretching that has been happening since the first fraction of a second after the Big Bang, will have done its work so thoroughly that our galaxy, and perhaps the small clutch of galaxies gravitationally bound to it, will be the only things that exist within the observable universe. An island, not metaphorically, literally. This is not a prediction made by pessimists or doomsayers. It is the straightforward conclusion of mainstream cosmology. The universe is not just expanding, it is accelerating. Something cosmologists call dark energy is pushing space apart at an increasing rate, and that rate shows no sign of slowing. The math has been run by some of the most careful minds in the history of science, and the answer it keeps producing is this. The universe is not a place that stays. It is a place that leaves. And here is the twist that makes this more than a story about the far future. The universe has already started. Other galaxies are already accelerating away from us. Some have already crossed the horizon. Some of the lights we see in the night sky tonight are the last photons from sources that, in the truest physical sense, no longer exist within our reachable universe. We are already living in a cosmos that is, slowly and without drama, going dark around us. The last humans won't be the first to experience this. We already are. We're just too early in the process to feel it yet. To understand how we arrived at this conclusion, this strange, vertiginous discovery that the universe is not merely vast, but actively retreating, you have to go back to a specific night, in a specific city, at a specific moment when the world was still small enough that one person with a telescope could change everything humanity thought it knew about the scale of existence. The year is 1912. The place is Flagstaff, Arizona. The Lowell Observatory sits on a mesa above the town, built by a wealthy Bostonian named Percival Lowell, who was, depending on your generosity, either a visionary or a man whose enthusiasm routinely outpaced his evidence. Lowell had become famous, and to serious astronomers, somewhat notorious, for his conviction that the dark lines he observed on Mars were canals, engineered waterways built by a dying Martian civilization. The scientific establishment was largely skeptical, but the observatory he built to chase that dream was real, and the instruments inside it were genuinely excellent. And it was there that a young astronomer named Vesto Slipher sat down at a spectrograph on the night of September 17th, 1912, and pointed it at a faint smudge of light in the constellation Andromeda. That smudge was known at the time as the Andromeda Nebula. The word nebula simply meant cloud, a fuzzy object in the sky that wasn't a star and wasn't a planet and wasn't a comet. Nobody knew what it was, precisely. The leading assumption was that these nebulae were clouds of gas within our own galaxy, perhaps solar systems in the process of forming. The universe, as far as anyone understood in 1912, consisted of one galaxy, the Milky Way, and everything in the sky was part of it. The idea that there might be other galaxies, other entire collections of hundreds of billions of stars existing beyond our own, was not yet a serious scientific proposition. It was, if anything, the kind of speculation that respectable astronomers politely avoided at dinner. What Slipher was trying to do that night was far more modest than cosmology. He simply wanted to measure how fast the Andromeda Nebula was rotating by studying the Doppler shift in its light, the same principle that makes an ambulance siren change pitch as it passes you. Light from objects moving toward you gets compressed into shorter, bluer wavelengths. Light from objects moving away from you gets stretched into longer, redder ones. Slipher expected to find a gentle rotation. Instead, he found something that made him check his equipment twice, then check it again. The Andromeda Nebula was moving toward us. That was surprising but not impossible. What was staggering was the speed. It was approaching at approximately 300 kilometers per second. No object in the known universe had ever been measured moving that fast. Slipher stared at his results with the kind of careful disbelief that good scientists deploy when the data starts doing something the textbooks haven't accounted for. He spent months refining the measurement before he trusted it enough to report. He presented his findings to the American Astronomical Society in August 1914, just as Europe was stumbling into the First World War and most of humanity's attention was pointed very much downward. The reception from his colleagues was immediate and striking. The audience stood and applauded. In a room full of people whose professional lives were dedicated to careful, incremental discovery, something about Slipher's numbers had landed like a stone through glass, and nobody was entirely sure what it meant, but everyone in that room understood that it meant something. Over the next decade, Slipher kept working. He measured the velocity of spiral nebula after spiral nebula, and the pattern that emerged was disquieting. Almost all of them were moving away from us. not just moving away, hurtling away at velocities that dwarfed anything observed within our own galaxy. By the early 1920s, he had measured 41 spiral nebulae, and 36 of them were receding. The redshifts were enormous. Something was happening that existing science had no framework to explain. The framework arrived, with typically dramatic timing, from a man who was simultaneously a boxer, a basketball player, a Rhodes Scholar, a soldier, and one of the most consequential astronomers in human history. Edwin Hubble was not by any measure a modest man. His colleagues found him brilliant and insufferable in roughly equal measure. But in October 1923, working at the Mount Wilson Observatory in California with the most powerful telescope then in existence, a 100-inch reflector that had taken years to build and required a team of men to operate, Hubble made a measurement that broke the universe open. He was examining photographic plates of the Andromeda Nebula, and on one of those plates he identified a specific type of pulsating star called a Cepheid variable, a star whose brightness rises and falls in a regular cycle, and whose cycle length is directly tied to its true luminosity. Astronomer Henrietta Swan Leavitt had discovered this relationship a decade earlier, working painstakingly through thousands of photographic plates at the Harvard Observatory, a woman doing work that the institution classified as that of a skilled computer rather than a scientist, paid 25 cents an hour for calculations that would eventually help rewrite cosmology. Leavitt's period luminosity relationship was the key that Hubble now used to measure distance. If you know how bright a star truly is, and you can measure how bright it appears from Earth, the difference tells you exactly how far away it is. Hubble measured his Cepheid. Then he measured the distance it implied. The Andromeda Nebula was not a cloud of gas inside our galaxy. It was a galaxy in its own right, almost 1 million light-years away, a number so far beyond the expected scale of the universe that Hubble reportedly stared at his calculation for a long time before writing anything down. He crossed out the letters NB he had originally written on the photographic plate, short for nebula, and replaced them with a single word, VAR, variable, the mark of certainty, the moment the universe became unimaginably larger than it had been the day before. By 1929, combining his own distance measurements with Slipher's velocity data, Hubble published the relationship that would eventually carry his name. The further away a galaxy is, the faster it is receding from us. This was not a local accident. It was not the result of one galaxy having a peculiar motion. It was a universal law written in the light of every galaxy in every direction of the sky. The universe was expanding. Everything was moving away from everything else. Space itself was growing. Hubble thought he understood what he had found. In truth, he had only found the beginning of the question. So let's try to actually hold this in our minds, not just accept it as an interesting fact and move on, but genuinely feel the scale of what we're talking about. Because the numbers involved in cosmic expansion are the kind that the human brain is simply not built to process without help. We evolved to judge distances in savanna grass and forest canopy. We are not naturally equipped for this. So let's build it slowly. Start with something familiar. The distance from London to New York is roughly 5,500 kilometers. It takes about 7 hours in a commercial aircraft traveling at cruising speed. That feels like a long way. It is, by human standards, a significant journey. Now consider that the Moon is about 385,000 kilometers away, roughly 70 times that transatlantic journey. The Apollo astronauts covered that distance in about 3 days, which still strikes most people as remarkably fast until you start extending the comparison outward. The Sun is 150 million kilometers away. If you drove there in a car at motorway speed, without stopping, it would take you approximately 170 years. Light, traveling at 300,000 kilometers per second, the fastest anything in the universe is permitted to move, covers that same distance in about 8 minutes. And light speed is the measuring stick we use once distances get truly serious, because kilometers become useless almost immediately. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That means the light arriving from it tonight left its surface 4.2 years ago. If Proxima Centauri vanished right now, we wouldn't know for more than 4 years. Our galaxy, the Milky Way, is approximately 100,000 light-years across. If the entire solar system, Sun, planets, the vast emptiness between them were shrunk to the size of a coffee cup, the Milky Way at the same scale would be roughly the size of the continental United States. Every star you have ever seen in the night sky is inside that coffee cup-scaled solar system. The galaxy around it is America. Now here is where the scale starts to genuinely strain comprehension. The Andromeda galaxy that Hubble measured, our nearest large galactic neighbour, is approximately 2.5 million light-years away. The light reaching your eyes from Andromeda tonight is 2.5 million years old. It left its source when our ancestors were early Homo species wandering the African savanna, before stone tools, before fire, before anything that resembles human civilization had the faintest hint of beginning. That light has been travelling through empty space ever since, and it is only now arriving. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter, not 93 billion years old, 93 billion light-years across. The difference matters enormously. The universe is only about 13.8 billion years old, but because space itself has been expanding during all the time that light has been travelling, the objects that emitted the oldest light we can see are now much farther away than the light travel time would suggest. The universe has been stretching the whole time. Within that observable sphere, current estimates suggest there are roughly 2 trillion galaxies. 2 trillion. If you counted one galaxy per second, without sleeping, without stopping, it would take you 63,000 years to count them all. And each of those galaxies contains, on average, hundreds of billions of stars. The Milky Way alone contains somewhere between 100 and 400 billion. If every star in the Milky Way were a grain of sand, you would have enough sand to fill roughly 10,000 beaches the size of Copacabana. Now hold all of that, every beach, every grain, every galaxy, every trillion-year journey of ancient light, and consider this. The observable universe is not the whole universe. It is merely the part we can see. The actual universe almost certainly extends far beyond that 93 billion light-year boundary, possibly infinitely, in directions from which light has simply not had enough time to reach us yet. We are living inside a bubble of visibility, surrounded by a reality we cannot, even in principle, observe. The edge of the observable universe is not a wall. It is a horizon. Like the horizon at sea, the limit of your view, not the edge of the ocean. And that horizon is shrinking, not quickly enough for any human lifetime to notice, not quickly enough for any civilization lasting thousands of years to measure with the naked eye. But the acceleration of cosmic expansion means that galaxies beyond a certain distance, roughly 14 billion light-years from us, a boundary called the Hubble radius, are already receding faster than light can cross the gap. They are not technically moving through space faster than light. Space itself between us and them is growing fast enough that the light they emit can never reach us. They are, for all practical and physical purposes, gone. Already. Tonight. The local group, the cluster of galaxies gravitationally bound to the Milky Way, including Andromeda and a few dozen smaller companions, is roughly 10 million light-years across. It is the only part of the universe that gravity will eventually pull together, rather than allow dark energy to scatter. Everything outside it is, on a long enough timescale, already lost. Our cosmic neighborhood, surrounded by an expanding void that will one day be the entirety of what the last humans can observe, is roughly 10 million light-years wide. In a universe 93 billion light-years across, that is the equivalent of a single coffee cup sitting alone in the middle of a continent. And it is getting lonelier every second. To understand why the last humans will be cosmologically alone, you need to understand what is actually doing the pushing, because the expansion of the universe is not, it turns out, a simple thing. It is not like an explosion, where debris flies outward from a central point and gradually slows as it loses energy. It is something stranger, something that took the smartest people in the world most of the 20th century to even begin to characterize properly, and something that we still, if we are being completely honest, do not fully understand. To get there, you have to start not with telescopes or supernovae or billion-dollar space observatories. You have to start with a man sitting alone in a patent office in Bern, Switzerland, in 1905, thinking about light. Albert Einstein was 26 years old and working as a technical examiner, a clerk essentially, and reviewing other people's patent applications, when he published 4 papers in a single year that collectively rearranged the foundations of physics. The one that would eventually matter most for our story came 10 years later. In November 1915, Einstein published his general theory of relativity, and it was a complete reimagining of what gravity actually is. Before Einstein, gravity was a force. Newton had described it as an invisible pull between masses across empty space, instantaneous, universal, mysterious in its mechanism, but reliable in its mathematics. It worked. It predicted planetary orbits to extraordinary precision. It was, for more than 2 centuries, considered essentially complete. Einstein replaced that picture with something more geometric, and once you spend enough time with it, more beautiful. In general relativity, the massive objects do not pull on each other across space. They bend space itself. The Earth does not orbit the Sun because the Sun is pulling it with an invisible rope. The Earth follows the curve that the Sun's enormous mass creates in the fabric of space-time, the way a marble rolls around the inside of a bowl, not because the bowl is pulling it, but because the bowl has a shape. Gravity is not a force. It is a geometry. Mass tells space how to curve, and curved space tells mass how to move. Now here is the part that immediately gave Einstein a headache he was not expecting. When he applied his new equations to the universe as a whole, treating all of space and all of matter as a single system, the mathematics refused to produce a static result. The equations kept insisting, with the relentless indifference of mathematics to human preference, that the universe must be either expanding or contracting. It could not sit still. Any static solution was unstable, like a pencil balanced on its point. The slightest perturbation and it would tip. This was 1917, more than a decade before Edwin Hubble had made his measurements, and the scientific consensus, shared by Einstein himself, was that the universe was eternal and essentially unchanging. The idea of a universe in motion struck him as almost certainly an artifact of the mathematics rather than a description of reality. So he did something that he would later call the greatest mistake of his life. He added a term to his equations, an arbitrary mathematical constant, which he called the cosmological constant, represented by the Greek letter lambda. Its sole purpose was to act as a kind of repulsive pressure that would counterbalance gravity at cosmic scales and hold the universe steady. He was not describing something he had discovered in nature. He was not proposing a new physical substance or force with any theoretical justification. He was patching an equation to make it behave the way he assumed reality must behave. It was, for all its mathematical elegance, a fudge. Then Hubble published his results in 1929. The universe was expanding. Einstein's original equations had been right all along. The cosmological constant was unnecessary. Worse than unnecessary, it was an embarrassment. Einstein reportedly visited Hubble at Mount Wilson Observatory, examined the data carefully, and abandoned the constant entirely, publicly describing it as his greatest blunder. The universe was not static, it was growing. And if you ran that growth backward in time, like rewinding a film, everything converged toward a single point of incomprehensible density at a finite moment in the past. What we now call the Big Bang, though that name came later, coined somewhat dismissively by the astronomer Fred Hoyle, who didn't actually believe it. For the next several decades, the central question in cosmology seemed straightforward, at least in its framing. The universe was expanding. Gravity was working against that expansion, pulling all matter back toward all other matter. The question was simply, which force would win? Would gravity eventually overcome the expansion, slow it to a halt, and reverse it into a catastrophic big crunch? Or would the expansion slow asymptotically, the universe coasting forever toward infinite thinness, stars gradually dying, everything spreading out into a cold and featureless darkness? The answer seemed to depend entirely on one number, the average density of matter in the universe. More matter meant more gravity, meant more deceleration. Calculate the density precisely enough, and you could, in principle, calculate the fate of everything. This is what makes what happened in 1998 so extraordinary. Two independent teams of astronomers set out to measure that deceleration directly and found something that neither team expected, that nobody in the field had seriously prepared for, and that took years for the broader scientific community to fully accept. To understand what they found, you need to understand the tool they were using. A Type 1. A supernova occurs when a white dwarf star, the dense collapsed remnant of a dead sun, roughly the mass of our sun compressed into a sphere about the size of Earth, has a companion star close enough that it can steal material from it. As the white dwarf accumulates mass, it approaches a critical threshold of approximately 1.4 times the mass of our sun. This threshold is known as the Chandrasekhar limit, named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930 at the age of 19 while on a steamship from India to England, which is the kind of detail that makes you question your own productivity. When the white dwarf crosses that limit, it detonates in a thermonuclear explosion, so powerful it briefly outshines its entire host galaxy. The crucial property of these explosions, for astronomical purposes, is their consistency. Because they always detonate at approximately the same mass, they always release approximately the same amount of energy. They are, in the language of observational astronomy, standard candles, objects whose intrinsic luminosity you know in advance. And if you know how bright something truly is, and you can measure how bright it appears from Earth, the inverse square law of light tells you exactly how far away it is. A standard candle twice as far away appears 4 times fainter. The mathematics is clean. The technique is reliable. And Type 1a supernovae are bright enough to be visible across billions of light years, making them the most powerful distance measuring tools available to cosmologists studying the large-scale universe. Both teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other led by Brian Schmidt and Adam Rees, then at Harvard, were measuring dozens of these supernovae in distant galaxies and comparing their distances to their recession velocities, building a detailed picture of how the universe's expansion rate had evolved over time. The expectation shared by virtually everyone in cosmology was that they would measure deceleration. Some deceleration. The only open question was its magnitude. Was there enough matter in the universe to eventually reverse the expansion, or merely enough to slow it? Both teams expected to answer that question. Neither team expected to find that the question itself was based on a false premise. The distant supernovae were fainter than they should have been. Both teams found it. Neither team wanted to find it. The result went through months of checking, rechecking, searching for systematic errors, instrumental biases, contamination from dust, errors in the standard candle calibration. The faintness survived every test. And faintness for a standard candle means only one thing. The supernovae were further away than the models predicted, not slightly further. Measurably, consistently, reproducibly further. The universe had not been decelerating, it had been accelerating. The expansion of space was not slowing down under the influence of gravity, it was speeding up. Something was pushing space apart with increasing force, and that force was winning over gravity at cosmological scales. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011. The discovery is still considered one of the most significant in the history of science, not because it answered a question elegantly, but because it revealed that the question we had been asking was the wrong one entirely. The thing doing the pushing acquired a name almost immediately, for the same reason doctors name diseases before they understand them. It is easier to discuss something if you can point at it. Dark energy. It is called dark not because it is dangerous or mysterious in a dramatic sense, but because it emits no light, reflects no light, and interacts with ordinary matter in no way we can currently detect. We know it exists because of what it does to the geometry of space-time at cosmic scales. We know almost nothing else about it with confidence. Current measurements from the Planck satellite and other instruments suggest it constitutes approximately 68% of the total energy content of the observable universe. All ordinary matter, every star, every planet, every galaxy, every human being, every atom of everything we have ever observed, theorized, or built instruments to detect, accounts for roughly 5%. The remaining 27% is dark matter, a separate invisible substance inferred entirely from its gravitational effects on the rotation of galaxies and the large-scale structure of the universe. We live, in other words, in a universe whose composition is 95% unknown to us. The periodic table, all of chemistry, all of particle physics, everything we have used to build our entire model of reality, is a description of 1/20th of what exists. The universe is looking at us with 95% of its face covered. The leading theoretical candidate for dark energy is something called vacuum energy, the idea, emerging from quantum mechanics, that empty space is not actually empty. At the quantum scale, the Heisenberg uncertainty principle states that you cannot simultaneously know the energy of a system and how long it has had that energy with perfect precision. The consequence of this is that pairs of virtual particles, a particle and its antimatter partner, are constantly flickering into existence in the vacuum, existing for the briefest possible moment, then annihilating each other and returning their borrowed energy to nothing. This process gives the vacuum itself a kind of baseline energy density, a pressure inherent to space that does not dilute as space expands. It is simply a property of space, the energy cost of existence per unit volume. And as the universe grows, more space means more of this energy, which drives more expansion, which creates more space, which creates more energy. A feedback loop built into the structure of reality. Einstein's cosmological constant, the term he added to hold the universe still and then abandoned in embarrassment, turns out to be mathematically equivalent to exactly this kind of vacuum energy. The constant he called his greatest blunder may, with a degree of irony that would have delighted him and infuriated him simultaneously, be the most physically real term he ever wrote down. But here is where genuine intellectual honesty requires a pause. When physicists calculate the expected magnitude of vacuum energy using quantum field theory, our best theory of matter and energy at the smallest scales, and compare it to the observed magnitude of dark energy inferred from the supernova measurements and the cosmic microwave background, the two numbers disagree. Not slightly, not by an order of magnitude, by a factor of approximately 10 to the power of 120. That is a 1 followed by 120 zeros. To give you some sense of what that discrepancy means, the number of atoms in the observable universe is estimated at around 10 to the power of 80. The mismatch between our best quantum theory and our best cosmological observation is larger than the number of atoms in everything we can see. It is, without any serious competition, the largest discrepancy between theory and observation in the entire history of science, and it sits at the center of our understanding of why the universe is tearing itself apart. Nobody knows how to resolve it. Several approaches have been tried. None has worked. The problem has a name, the cosmological constant problem, and it is sometimes described by physicists as the worst theoretical prediction in the history of physics. What we do know, with confidence born from multiple independent lines of evidence, is the consequence of dark energy's dominance. With expansion accelerating, galaxies beyond our local group recede faster and faster. The light they emit has an increasingly difficult journey to reach us, stretched to longer and longer wavelengths as it travels across expanding space. Eventually, for galaxies beyond a certain distance, the expansion of the intervening space outpaces the speed of light itself, not because anything is moving through space faster than light, which relativity forbids, but because space itself is growing fast enough that the distance between us and the light source increases faster than the light can cross it. These galaxies do not disappear. They are still there, but they become permanently, physically unreachable. No signal they emit will ever reach us again. No signal we emit will ever reach them. The information is not destroyed. It is simply placed forever on the other side of a one-way door. This boundary, the cosmic event horizon, is already real, already operative, already cutting us off from galaxies we can currently observe. The light we see from the most distant galaxies tonight is, in a very real sense, a farewell. Those galaxies have already crossed the horizon. We are watching their past. Their present is unreachable, and their future is, from our perspective, simply gone. Stars will continue to burn, of course. The longest-lived red dwarf stars, tiny and cool and extraordinarily conservative with their hydrogen fuel, can sustain nuclear fusion for up to 10 trillion years, roughly 1,000 times the current age of the universe. But one by one, across timescales that make all of recorded human history look like a single heartbeat in a very long life, they will exhaust their fuel, collapse, and go dark. What remains in the far future will be an island galaxy, Milkomeda, the merged remnant of the Milky Way and Andromeda, populated by black holes, cold neutron stars, and the dark cinders of dead suns, and orbiting a common gravitational center in a universe with no other light source visible anywhere in any direction of the sky. And somewhere in that darkness, if anything resembling a mind still exists, it will look up and see nothing, and know, in whatever way such a mind knows things, that it is the last light in the only universe it will ever be able to reach. Which raises a question that is, in its own way, more unsettling than the darkness itself. How certain are we really that this is what's coming? Because the entire picture depends on measurements made across distances and timescales that stretch the word confidence to something approaching its breaking point. Here is the honest version of what we actually know, as opposed to what we present with the confident cadence of settled science. And the honest version is considerably more uncomfortable. Every measurement underpinning the story of cosmic acceleration, Every data point that feeds into our picture of dark energy, the fate of the universe, and the ultimate isolation of the last humans depends on instruments pointed at objects billions of light years away, interpreting signals that have been traveling through expanding, warping, absorbing space for longer than the Earth has existed. We are not reading the universe directly, we are reading its light. And light, it turns out, is an imperfect messenger in ways that are genuinely difficult to fully account for. Take the Type 1a supernovae that earned Perlmutter, Schmidt, and Rees their Nobel Prize. The standard candle assumption that all Type 1a supernovae detonate at roughly the same intrinsic brightness is well supported but not perfectly uniform. These explosions occur in a variety of galactic environments with different chemical compositions, different surrounding gas densities, different evolutionary histories. Astronomers apply corrections for these variations, and those corrections are carefully constructed from decades of observation. But the corrections are models. They are our best approximation of what is happening inside an explosion occurring in a galaxy 6 billion light-years away. The possibility that distant supernovae, occurring in the younger, chemically different universe of billions of years ago, behave systematically differently from nearby ones in ways our corrections do not fully capture. That possibility has not been eliminated. It has been studied, constrained, argued over, and deemed unlikely by most experts. But unlikely is not the same as ruled out, and the entire edifice of our understanding of dark energy rests, in part, on that assumption holding. Then there is the problem of what dark energy actually is, which is not merely a gap in our knowledge, but a gap so large it has started to look less like a gap and more like a canyon. The cosmological constant interpretation, vacuum energy as the driver of acceleration, produces that catastrophic mismatch of 10 to the 120th power between theoretical prediction and observation. Several alternative models have been proposed. Quintessence is one, the idea that dark energy is not a fixed property of space, but a dynamic field that evolves over time, potentially changing its strength as the universe ages. If quintessence is correct, the future we have described might be wrong. The acceleration might slow, it might reverse. The universe's fate would be fundamentally different from the Big Freeze, and our picture of the last human's isolation would need to be redrawn entirely. Other theorists have proposed modifications to general relativity itself. The suggestion that Einstein's framework, while extraordinarily accurate at solar system scales and even galactic scales, breaks down at cosmological distances in ways that mimic the appearance of an accelerating expansion without requiring any dark energy at all. These modified gravity theories are, to be fair, significantly less favoured by the current evidence than the cosmological constant model. But they are not dead. They are live scientific proposals with serious researchers working on them, and the fact that they exist at all should remind us that our current model is a model, not a photograph. There is also a subtler problem that tends to get less attention in popular accounts of this subject. The measurements that constrain dark energy, the supernova surveys, the cosmic microwave background observations, the baryon acoustic oscillation data, all assume that the universe is, on the largest scales, roughly the same in every direction. Homogeneous and isotropic in the technical language. This assumption is well supported by the evidence we have, but testing it fully is genuinely impossible from our single fixed location in space. We can observe in every direction, but we cannot step outside the universe to verify that our local patch is representative of the whole. There is a real, if minority, scientific position that our local cosmic neighbourhood might be slightly underdense compared to the universe at large. A vast cosmic void that could, in principle, affect our measurements of expansion in ways that partially mimic the signal of acceleration. This is the Hubble tension adjacent to a deeper problem, and it is not resolved. Speaking of which, the Hubble tension. This is perhaps the most actively discussed crisis in contemporary cosmology, and it deserves a moment. The Hubble constant is the number that describes the current rate of cosmic expansion, how fast the universe is growing per unit distance. When you measure it using the cosmic microwave background, the relic radiation from the early universe mapped in extraordinary detail by the Planck satellite, you get a value of approximately 67 kilometers per second per megaparsec. When you measure it using the local universe, Cepheid variable stars, Type 1a supernovae, the distance ladder built up from observations of nearby galaxies, you get approximately 73. These two numbers disagree by enough that the probability of the discrepancy being a statistical accident is less than 1 in a million. Both measurements have been checked exhaustively. Both sets of researchers are confident in their methodology. The numbers simply don't agree. Either one measurement has an unidentified systematic error, or our standard model of cosmology is missing something fundamental. As of the time of writing, nobody knows which. And beneath all of this sits the most fundamental barrier of all. We cannot observe dark energy. We cannot detect it directly with any instrument we possess, or have any near-term prospect of building. We know it exists, or rather, we know that something is causing the observations we see, because of its gravitational effect on the large-scale structure of the universe. That is the entirety of our empirical handle on it. We are inferring the nature of 68% of the universe's content from its side effects, the way you might infer the existence of a very large animal you have never seen from the size of the footprints it leaves in soft ground. The animal is almost certainly real, but you do not know what it looks like, where it came from, whether it is one animal or many, or whether your interpretation of the footprints is entirely correct. What this means, in the most direct terms possible, is that the story of the last human's isolation, compelling and mathematically grounded as it is a projection built on a foundation that contains, at its very center, something we do not understand. The direction of the projection seems robust, the endpoint seems likely, but the confidence with which popular science sometimes presents the heat death of the universe as a settled fact is, if we are being rigorous, somewhat ahead of what the evidence strictly warrants. That is not a reason to dismiss the story. It is a reason to hold it with the kind of alert, curious uncertainty that makes science worth doing in the first place. Because the places where our knowledge develops cracks are not the embarrassments of science, they are its growing edges. And on the question of cosmic fate, those edges are very much alive. Let us travel forward in time, not in the science fiction sense of stepping into a machine and arriving somewhere else. In the sense of following the physics, step by step, era by era, watching what actually happens to the universe as dark energy does its slow, patient, inexorable work. Because the story of the last human's isolation is not a single event. It is a journey through time so vast that every scale comparison we have used so far becomes inadequate, and we need new ones. Think of the entire current age of the universe, 13.8 billion years, from the Big Bang to this moment, to you sitting here right now, as a single step, one step. What follows will require thousands of those steps, then millions, then numbers that have no common name. We begin, as all good journeys do, close to home, in the present. Right now, tonight, the night sky above you contains approximately 5,000 stars visible to the naked eye. All of them are in our galaxy. The Milky Way itself contains somewhere between 100 and 400 billion stars, most of them invisible to us individually, their collective light merging into that pale band across the sky that gave the galaxy its name. Beyond the Milky Way, the local group, our gravitationally bound cluster of roughly 54 galaxies, dominated by the Milky Way and Andromeda, stretches across about 10 million light-years. Beyond that, the Virgo supercluster connects us to thousands of other galaxies across a region roughly 110 million light-years wide. And beyond that, the observable universe extends in every direction, containing its 2 trillion galaxies, its hundreds of sextillion stars, its incomprehensible cargo of planets, gas clouds, black holes, and the thin, cold whisper of the cosmic microwave background radiation permeating everything like the last fading warmth of a fire lit 13.8 billion years ago. This is the universe at its richest. This is the peak, and we are, in a very real sense, living through it. The first thing dark energy will take from the future is not the stars themselves, it will be the view. Over the next few billion years, the galaxies of the Virgo supercluster and beyond will continue receding, their light redshifting toward longer and longer wavelengths. Their apparent brightness dimming not because they are dying, but because the expanding space between us is stretching their light into frequencies our instruments will struggle to detect. First the ultraviolet, then the visible, then the infrared, the microwave, the radio. Each frequency range going dark in sequence, like a musician's range narrowing note by note. Future astronomers, if there are any, will be able to detect these galaxies only with increasingly exotic instruments tuned to increasingly low-energy radiation. Then, eventually, not at all. But before that slow dimming reaches its conclusion, something far more dramatic will happen much closer to home. In approximately 4.5 billion years, the Andromeda Galaxy will arrive. This is not a metaphor or an approximation. Andromeda is currently approaching the Milky Way at roughly 110 kilometers per second, drawn by the mutual gravitational attraction between 2 of the largest galaxies in the local group. The collision, and calling it a collision, requires some qualification. Will be one of the most spectacular events in the future history of our corner of the universe. The qualification is this: galaxies are almost entirely empty space. The distances between individual stars within a galaxy are so enormous that when 2 galaxies interpenetrate, the probability of any 2 stars actually colliding is vanishingly small. It would be like firing 2 shotgun blasts at each other from a kilometer apart and expecting the pellets to hit each other in mid-air. The stars will pass through each other's company like ghosts. What will not pass through harmlessly is the gravity. The gravitational interaction between 2 galaxies of this size will be transformative. Computer simulations, run many times, with many different initial conditions, all producing broadly similar results, show the merger playing out over several billion years. First contact, then a dramatic distortion of both galaxies' spiral structures as tidal forces pull out long streamers of stars. A partial separation as the galaxies swing past each other and their momentum carries them apart temporarily. Then a second approach, a second interpenetration, more violent distortion. Then gradually, over billions of years of gravitational settling, the merger of the 2 into a single large elliptical galaxy. The beautiful spiral arms of the Milky Way, those sweeping structures of star formation and interstellar gas that have been the nursery of countless solar systems, including our own, will be gone. What remains will be a smoother, rounder, more diffuse structure. Astronomers call it Milkomeda, an informal portmanteau that somehow makes the death of our galaxy sound almost cozy. What happens to our Sun during all this? Almost certainly nothing dramatic. The Sun will be too old by then to be much of a sun at all. In about 5 billion years, it will exhaust the hydrogen fuel in its core and begin expanding into a red giant, likely engulfing Mercury and Venus and possibly Earth, before shedding its outer layers and collapsing into a white dwarf. A dense, slowly cooling ember about the size of the Earth, containing roughly half the original mass of the Sun. The solar system as a habitat will be over long before Andromeda arrives. Whatever Earth's story is, it ends earlier in this chronology. The galaxy merger is an event for whatever, if anything, has moved elsewhere by then. But let us continue the journey, because the merger is not an ending. It is a transition. Milkomeda will be a real galaxy, populated with billions of stars, many of them younger than our Sun is today, formed in the bursts of star formation that galactic mergers typically trigger as compressed gas clouds collapse under gravitational pressure. For a period after the merger, the new galaxy may actually be brighter than either of its predecessors, lit by a generation of newly formed, massive, luminous stars. It will be, in its way, a kind of renaissance. New suns born from the collision of two old stellar cities. But here is the detail that stops you cold if you think about it carefully. Milkomeda will form in a universe that is, by then, already deeply lonely. The great recession of the non-local group galaxies will be well advanced. The Virgo superclusters galaxies, the thousands of galaxy clusters beyond the local group, will have long since crossed the cosmic event horizon. The observable universe of any astronomer in Milkomeda will be shrinking, not catastrophically, not visibly from year to year or century to century, but measurably over millions of years. The number of observable galaxies will decline as more and more cross permanently beyond the horizon. The cosmic inventory will be thinning. Now step forward further. These skip past the remaining lifetime of Milkomeda's youngest stars. Move past the slow reddening of the galaxy as its brightest, most massive stars burn through their fuel fastest and wink out first. These blue and white giants living only millions of years, a mayfly's lifespan against the cosmic calendar. Move past the long quiet middle age dominated by yellow stars like our former sun, burning for billions of years each. Move into the era dominated by the red dwarfs. This is where the universe's timeline gets strange in a way that popular cosmology often undersells. Red dwarf stars are the most common type of star in the universe. They make up roughly 70% of all stars in the Milky Way. They are small, dim, and extraordinarily fuel efficient. The smallest of them, with masses around 8% of the Sun's, burn so slowly and so completely that they can sustain nuclear fusion for up to 10 trillion years. 10 trillion. At that point, the current age of the universe, 13.8 billion years, represents less than 0.2% of a red dwarf's total lifespan. We are cosmically very early. The universe is, by stellar standards, still in its youth. The red dwarf era, sometimes called the stelliferous era by cosmologists, will be the longest period of stable starlight the universe ever produces, and it will dwarf everything that came before it by a factor of roughly 1,000. During that immense span, if anything resembling civilization persists, it will exist in a universe growing progressively darker and quieter at its largest scales, but still, locally, warmly lit by the patient glow of red suns. Red dwarfs produce less ultraviolet radiation than our sun and more infrared. They burn with a dim reddish warmth, like embers rather than flames. Any planet orbiting in a red dwarf's habitable zone would need to be much closer to its star than Earth is to the Sun, close enough that tidal locking, where one face of the planet always faces the star as the Moon always faces Earth, would likely be a permanent condition. These tidally locked worlds would have a perpetual day side of warmth and light and a perpetual night side of cold and darkness, with a thin ring of temperate twilight running around their terminator. Strange worlds. Not Earth, but perhaps not uninhabitable. And here is one of those small, unexpected details that illuminates something much larger. The red dwarfs that will be burning 10 trillion years from now are already alive today. They are the dim, unremarkable dots that populate our galaxy's stellar census without ever making the highlights. Proxima Centauri, the nearest star to our Sun, is a red dwarf. It is not dramatic, it does not photograph well, but it will still be burning, quietly and patiently, long after every star like our Sun has collapsed into a white dwarf and begun its billion-year cooling into darkness. The future of life in this universe, if it has a future at all, belongs to the companions of these modest, overlooked suns. But 10 trillion years ends. Everything ends. As the last red dwarfs exhaust their hydrogen, they do not explode like more massive stars. They simply fade. Over billions of years, they contract slowly, their surfaces cooling from red to orange to infrared to nothing, becoming what astronomers call black dwarfs. Cold, dark, planet-sized masses of degenerate matter drifting silently through the void. The process is so slow, it defies any meaningful analogy, but it completes. And when the last red dwarf makes that final transition, the stelliferous era is over. What remains in the universe after the last star dies is not nothing. It is something in some ways stranger than nothing. The universe at this point, roughly 100 trillion years from now, will be populated by the dark remnants of dead stars. White dwarfs cooling toward black dwarfs over timescales of quadrillions of years. Neutron stars spinning down their rotational energy in solitude, and black holes. The black holes will be, by this point, the most significant structures in the universe. The supermassive black holes at the centers of galaxies, including the 4 million solar mass object at the center of what was once the Milky Way, will have consumed much of what drifted near them during the long stellar era. They will be enormous, and they will be, in a sense, the last lights, not emitting visible light, but radiating a quantum mechanical whisper of energy first theorized by Stephen Hawking in 1974. Hawking radiation is one of the most extraordinary theoretical predictions in the history of physics. It arises from the interaction of quantum mechanics and general relativity at a black hole's event horizon, where virtual particle pairs that flicker into existence near the boundary can be split, one falling in, one escaping, resulting in a net emission of energy from the black hole. The black hole slowly, over incomprehensible timescales, loses mass. A stellar mass black hole would evaporate via Hawking radiation in approximately 10 to the power of 67 years. A supermassive black hole of 1 billion solar masses would take approximately 10 to the power of 99 years. These numbers are so far beyond any human reference frame that the word years becomes almost meaningless. The current age of the universe is 10 to the power of 10 years. We are talking about timescales 10 to the power of 89 times longer than the universe has so far existed. But they end too. The last black hole evaporates, and what is left is a universe containing nothing but the thinnest imaginable gas of photons and fundamental particles, spreading endlessly through a space so cold it approaches absolute zero asymptotically, in a darkness so complete and so permanent that the word dark doesn't begin to reach it. This is the heat death, not an explosion, not a collapse. A whisper that gets quieter and quieter until there is no longer anything to make sound. Somewhere in the unimaginably long stretch between now and then, the last human, or the last thing that remembers being human, or the last thing that carries anything of what we were, will have drawn its final breath. And the question of exactly when that happens and under what circumstances leads somewhere unexpected. Because the physics of the far future contains at least one twist that almost nobody outside specialist cosmology knows about, and it reframes the entire story in a way that is genuinely and uncomfortably surprising. Here is the thing nobody tells you when they explain the fate of the universe. The story we have just travelled through, the accelerating expansion, the retreating galaxies, the dying stars, the evaporating black holes, the final silence, is not the story of what will definitely happen. It is the story of what will happen if dark energy remains constant. if the cosmological constant is truly constant. If lambda, that term Einstein added and then abandoned, and that the universe appears to have reinstated without asking anyone's permission, stays exactly the value it is today for the next 100 trillion years and beyond. There is no physical law that requires it to. This is the pivot, not a dramatic one, not announced with fanfare, but one that quietly dismantles the emotional architecture of everything you have just heard. Because the isolation of the last humans, the darkness of their sky, the loneliness baked into the geometry of their universe, all of it assumes that we have correctly characterized a substance that constitutes 68% of everything, that we cannot detect directly, that our best theory mispredicts by a factor of 10 to the power of 120, and whose fundamental nature remains, after more than 2 decades of intensive study, completely unknown. We have built a picture of the end of everything on a foundation we cannot see, cannot touch, and cannot explain. Think of it this way. Imagine you are trying to predict the weather for the next year. You have excellent instruments, you have sophisticated models, you have decades of historical data, and you can make reasonable short-term predictions with genuine confidence. But somewhere in your model, there is a variable, the single most important variable, the one that drives 68% of all atmospheric behavior, that you have never directly measured. You have inferred its current value from its effects. You have assumed it will remain roughly stable because it appears to have been roughly stable during the period you have been able to observe. And on that basis, you are confidently predicting the weather in 13 months' time to the hour. That is, approximately, the epistemic situation of modern cosmology with respect to the fate of the universe. The alternatives to a constant dark energy are not fringe ideas scratched on the back of an envelope by contrarians. They are serious, mathematically developed proposals being actively investigated by research groups at major institutions worldwide. Quintessence models, as mentioned earlier, propose that dark energy is a dynamic field that evolves over time. In some versions of quintessence, the field weakens over cosmic time, and the acceleration of expansion gradually slows. In others, it strengthens, leading to a scenario called the Big Rip, where the accelerating expansion does not merely push galaxies apart, but eventually tears apart galaxy clusters, then galaxies themselves, then solar systems, then planets, then atoms, in a sequence of escalating violence that ends the universe not in cold silence, but in a moment of infinite expansion where the fabric of space-time itself is shredded. In a Big Rip scenario, the last humans would not be alone in a dark but stable universe. They would be destroyed by the universe's own geometry, along with everything else, in a catastrophe that makes a supernova look like a struck match. Other models propose something called phantom energy, a form of dark energy whose density actually increases over time rather than remaining constant, making the Big Rip not merely possible, but inevitable. Current observational data cannot cleanly distinguish between a cosmological constant, quintessence, and phantom energy. The measurements are not yet precise enough. The differences in their predictions for the observable universe over the next few billion years are real but small enough to sit inside our current error bars, those honest brackets of uncertainty that every good measurement carries. And then there is the possibility that general relativity itself is incomplete, that our description of gravity at cosmological scales contains an error we have not yet identified, and that the apparent acceleration is not caused by any form of energy at all, but by a misapplication of equations that work brilliantly in the solar system and break down quietly when stretched to the scale of the observable universe. If this is true, the entire framework within which we have been making predictions about the far future needs rebuilding from the foundations. Here is the analogy that captures it. The sum total of what humanity has directly observed about the large-scale structure and fate of the universe. All our telescope data, all our satellite measurements, all our supernova surveys, all our cosmic microwave background maps covers a cosmic history of roughly 13.8 billion years, observed from a single point in space, using instruments that have existed for at most a few decades in their most powerful forms. The universe's projected future, on the other hand, extends for something in the region of 10 to the power of 100 years or more. Our observational window, expressed as a fraction of the timeline we are confidently projecting across, is so small it has no meaningful analogy in ordinary human experience. It is not like judging a film from its first frame. It is not like judging a human life from its first second. It is smaller than that. It is like judging the entire history and future of the Earth's climate from the temperature reading of a single thermometer on a single afternoon in a single garden, and then publishing a forecast for the next 4 billion years. What we have is not nothing. The physics is real. The measurements are genuine. The mathematics is sound within its assumptions. But the gap between what we know and what we are projecting across is so vast, so filled with the potential for unknown physics and unidentified variables, and the simple fact that nature has surprised us every single time we assumed we had reached the bottom of it, that the confidence with which the heat death is sometimes presented as the settled fate of the universe should give any honest thinker pause. The last humans may indeed look up into an empty sky, isolated beyond recovery, the final light in a universe gone dark. That is the most likely story the current evidence tells. But the universe has never once, in the entire history of our attempts to understand it, turned out to be exactly what we expected. It has always been stranger. It has always had one more layer. It has always, at the moment we thought we understood it, produced something that required us to begin again. The darkness at the end of everything may not be the end of the story. It may simply be the last thing we can currently see. Consider what we have managed to do as a species in the time we have been paying attention. We sent 12 human beings to walk on the moon using computers less powerful than the device in your pocket. We landed a rover the size of a car on Mars by lowering it on cables from a rocket-powered sky crane. A sequence of engineering decisions so audacious that the team that designed it called the entry, descent, IGA and landing phase the 7 minutes of terror, because once the sequence began, it was entirely autonomous, and everyone on Earth could only watch. We detected gravitational waves, ripples in the fabric of space-time itself, produced by two black holes merging more than 1 billion light-years away, using an instrument that can measure a displacement 1/10,000th the diameter of a proton. We mapped the human genome. We eradicated smallpox. We built the James Webb Space Telescope, folded it like origami into a rocket, launched it to a gravitational balance point 1 million miles from Earth, unfolded it flawlessly in the cold of space, and used it to photograph galaxies that formed within the first few 100 million years after the Big Bang. We are, by any reasonable measure, a remarkable species. And we still do not know what 68% of the universe is made of. That juxtaposition is not a criticism. It is, in a strange way, the most inspiring fact in science, because it means that the greatest discovery in human history has not yet been made. The question of what dark energy actually is, whether it is vacuum energy, a dynamic field, a modification of gravity, or something no theoretical framework has yet imagined, is not merely a cosmological curiosity. Its answer will determine whether the story of the last humans ends in isolation or in something else entirely. It will rewrite our understanding of space, time, matter, and the ultimate fate of everything that exists. The discovery of dark energy's true nature will be, if it comes, the moment that the Hubble expansion discovery, the Big Bang confirmation, and the detection of gravitational waves will all be footnotes too. It is the deepest open question the universe has handed us, and it is sitting there, patient and enormous, waiting. The tools we are building to approach it are remarkable. The Vera C. Rubin Observatory in Chile, when fully operational, will survey the entire visible southern sky every few nights, cataloguing billions of galaxies and millions of supernovae with a thoroughness that previous surveys could not approach. The Euclid Space Telescope, launched in 2023, is mapping the geometry of the universe across 10 billion years of cosmic history, with a precision designed specifically to constrain the behavior of dark energy over time. The Nancy Grace Roman Space Telescope will extend the supernova survey that Perlmutter, Schmidt, and Rees began, pushing the standard candle measurements to greater distances and earlier cosmic epochs. These are not marginal improvements on existing instruments. They are generational leaps in our ability to read the universe's autobiography. What they find will matter beyond cosmology. If dark energy turns out to be genuinely dynamic, if it has changed over cosmic time and will change again, then the future we have described is not fixed. The isolation of the last humans is not guaranteed. The darkness is not predetermined. The universe may have turns in its story that our current chapter cannot see. And if dark energy turns out to be exactly what the cosmological constant suggests, unchanging, permanent, the baseline energy of space itself, then we face a different kind of challenge. Not a cosmological one, but a philosophical one. What does it mean to be a civilization that knows its ultimate fate? What does it mean to persist, to create, to love, to build, to reach outward with telescopes and probes and radio signals in the full knowledge that the universe is slowly, irrevocably withdrawing the very light it once offered so generously? Perhaps it means exactly what it has always meant. Humans have always known they were mortal. Individual mortality has never, in the long run, stopped a single generation from planting trees whose shade they would never sit in. The knowledge that our sun will die in 5 billion years has not prevented anyone from falling in love, writing a symphony, or staying up too late watching a documentary about the end of everything. Civilizations are made of exactly that, the refusal to let the scale of what we cannot control diminish the weight of what we can. The last humans will be alone in a way we cannot fully imagine. Their sky will be dark in a way ours is not. Their universe will be smaller, colder, and quieter than the one we inherited. But they will still be here, still looking up. Still, in whatever way such beings look, wondering what is out there beyond the darkness, and whether anyone else has ever asked the same question. That impulse, the looking up, the asking, the refusal to accept the horizon as an answer, is the most human thing there is. It is what sent Vesto Slipher to his spectrograph on a September night in 1912. It is what drove Henrietta Leavitt through thousands of photographic plates for 25 cents an hour. It is what Hubble felt when he crossed out NB and wrote VAR. It is what Perlmutter and Rees and Schmidt felt when the numbers came back wrong and they checked them again anyway. The universe is leaving. It has been leaving since the beginning, and we have spent 100 years learning to read the light it leaves behind. Whatever we discover next, in the dark between the galaxies, will be the most important thing we have ever found. And we have barely started looking.